Okay, the recording is starting. If you have anything private that you want to discuss, we can do that after I start the recording. Actually, it's probably going to be preferred method to log in. Is this convenient for me to do it this way? All right, this computer is weird. I don't know what's going on with that. It's been processing the same. Okay, you guys should be able to see my screen shortly. And whenever you do, could you just give me a raised hand? You can see the screen. Okay, I see a couple of hands raised. Great. All right, I'm just waiting for the PowerPoint to open. Yep, I know iMirror is not working. I didn't ask for it. Okay, while we wait for the PowerPoint, I'll just start to talk. All right, alcohols. We're gonna start thinking about reactions to alcohols. The first unique thing that you guys know when you think about reaction chemistry, there's something called a nucleophile and typically an electrophile. Can you guys tell me what that means? What's a nucleophile? What's a nucleophile and what's an electrophile? So when we think of reactions, that's kind of where you guys should be at right now. We should know where nucleophiles are. If we're trying to do some type of reaction, we should know where the electrophiles are. Anyone wants to chime in? Okay, the word phile means to love, right? So if I'm a nucleophile, I love what, you think? A nucleus, right? And what's unique about the nucleus? It has what type of charge typically? A positive charge, right? Because in the nucleus is what? Protons, right? Neutrons have no charge, but protons do have a charge, right? So nucleophiles prefer positive regions, right? And you guys know very classical positive carbon reactive species, and what do you think that's called? A carbon cation, right? You guys remember how to make carbon cations? So carbon cations are definitely looking for nucleophiles, right? Nucleophiles attack carbon cations, all right? But nucleophiles also attack regions that are delta positive. So there's a polar bond, like there's an alkyl halide, I'm gonna attack the carbon and knock out the leaving, right? So nucleophiles hit those type of carbons, okay? So alcohols conveniently fall within a class of being a nucleophile or an electrophile. I'll get you guys to help me define that shortly. The opposite end of the spectrum is an electrophile. And the word phile, again, means to love. So if I'm an electrophile, I love what? Electrons, right? So that means I'm looking for somebody to donate electrons to me, right? So that means that typically nucleophiles donate electrons to who you think? Electrophiles, right? So the carbon cation will be classified as an electrophile. It's looking for electrons. It doesn't have all the electrons that it needs, okay? So if I had to look at an alcohol, and this is what chapter 11 is working with, would you classify an alcohol as a nucleophile or an electrophile? Nucleophile, okay, very good. Alcohols are typically nucleophiles. And how do I know that? What characteristics cause me to think that alcohols are nucleophiles? Okay, good. The oxygen on alcohols are electronegative, and that oxygen on an alcohol contains what? That's where. Yes. Okay. So the oxygen in alcohols contain what? There's something that the oxygens contain. We usually just put 4 dots. What are those things? Lone pairs, right? So oxygens on alcohols contain lone pairs, and those lone pairs are going to be nucleophilic, all right? So that's why alcohols are generally thought of as being nucleophilic. So there's going to be a reaction, there's going to be a class of reactions to alcohols that happen in O. I'm going to call these reactions at O, right? So that means that there's a lot of different ways that the oxygen in alcohols gain different things, right? Instead of having an OH, I can have an OR, I can have an O carbonyl, I can have an O carbon. I can make a lot of different things, okay? So that's a potential class of alcohols, is reacting at the oxygen, all right? So if you want to write that down, our first reaction at alcohols are going to be reacting at the oxygen, okay? So I'm going to use the O lone pairs to do chemistry, right? Reacting at the O. Right? So if I have an alcohol, I can react at the oxygen. I'm going to use the lone pairs to do chemistry. All right? So that's a class of reactions that we're going to start to learn this semester. Okay? Very classically, and we had to work on this here shortly. If my slides will work correctly. I don't know what's going on. Okay, I see what happened. I see what happened. Let me see. There we go. There we go. Okay. Another thing that oxygen or alcohols do is called oxidation or redox chemistry. All right. So what is redox? What does that mean? Yep. So redox means reduction oxidation. All right. We'll talk about that as well this semester. So an alcohol or carbon with an O has the ability to be oxidized. All right. And if we oxidize further, those oxidized compounds can be reduced back down, right? So we're going to work on that spectrum, moving up in oxidation and moving back down. Okay. So that's another class of reaction that can happen at alcohols. All right. They have let's use this slide to kind of cover this really quickly. So, alcohol reactions, they have first dehydration to alkene. We'll cover that. Typically an E1 process, right? You guys already know eliminations, right? So in the right conditions, you can eliminate an alcohol from alkene. All right, you can oxidize. We just talked about this, all right? This is going to be the meat of this chapter, oxidizing. All right, I don't know what's going on. Give me a sec. My PowerPoint slides have a mind of their own right now. What is up with this thing? Okay, I can do a substitution. So instead of having ROH, I can now have R halide, which would be R bromide, R chloride, R iodine, or R fluoride. All right, so we'll talk about substituting. We can substitute the OH for something else.
Let's say you get a little closer to the mic when you speak.
Okay. Oh, you guys cannot hear me. Okay, can you guys hear me better now? I'm sorry, I've been moving around back and forth.
Yeah,
you
yes.
guys hear me better now? Okay, good. I'll start over again. Reactions to alcohols. These are the kind of classifications that we want to use. I'm going to give you guys another way to do this, I think a little bit easier than this, but this is fine. This is a great list, all right? First is dehydration reactions, all right? What does it mean to dehydrate? I'm losing what? Water, right? So if you think about an alcohol, is it possible to lose water? Sure, right? There's an OH bond there, right? and I just need to lose one more what to get water? One more H, right? So if I lose an OH and another H, I've lost water, and that's going to generate an alkene, okay? I can have an alcohol, and I can oxidize it to an aldehyde or a ketone, all right? And you guys do know what aldehydes and ketones are, right? They typically contain a carbonyl. What's a carbonyl? A carbon-oxygen double bond, okay? So when we oxidize alcohols, we gain a bond to oxygen. We'll talk about those shortly as well, okay? We can do substitution reactions to form alkyl halides. We can do reductions to form an alkane. We can do esterification. We can do tosylation, and we can do a Williamson ether synthesis. And those last three reactions fall into the class of reactions at O, all right? So I'm getting some weird looks in class, so that gave me a mind to just open up ChemDraw. Let's draw this out for you guys' notes. Okay, so give me a sec here. We'll make some notes here live. Okay, oh, well, the next slide did a good job, actually. Maybe we'll still work in PowerPoint. I mean, we'll still work in ChemDraw once it comes up. All right, so this is a summary slide of all those processes. Again, if I have ROH, I can dehydrate to form alkenes, right? I can have ROH again and oxidize to form aldehydes and ketones or carboxyl acids. ROH could be substituted for alkyl halides. They can be reduced to alkanes, or I can do this reaction at O to form esters, tosyl groups. We'll talk about tosylation here shortly, and ethers, okay? And Williamson ether process has these two steps in order. First, you have to form the alkoxide, then you have to do a SN2 reaction with an alkyl halide to form an ether. Yep, and these are the publisher slides. Those slides are from the publisher. All right, I'm gonna go ahead and start making our notes in class today. So let's do this. This is reactions, alcohols. It's big. All right, we're gonna say dehydration. The first class of reactions. Let's make that a little bit bolder. All right, I'm going to put this down here so that we have a reference. This is chapter 11 textbook. All right, so let's just think about a dehydration. What is this? So I'm going to write some notes here for dehydration. Dehydration is just a loss of water. And this is from a molecule that contains alcohol, right? And if you want to think about the mechanism here, because we will need to know the mechanism for this process. This mechanism is a classic E1 mechanism. What's unique about an E1 mechanism? Can anybody tell me really quickly? There's some unique features to an E1 mechanism. Okay, different figures. I think I know what you're trying to say, but I need some more details.
Elimination, 2 steps.
There we go. There we go. Very good. Who's that? Who's saying that? Who said that?
Miss Holloway.
Miss Holloway. There you go. Good. Very good, Miss Holloway. Very, very good. Thank you. I'm going to type it in, but she definitely said what we needed to know here. An E1 process always occurs in 2 steps. All right. So this is a 2-step mechanism. All right. So what is step 1 of an E1 process? The leaving group leaves. That's right. All right. And this always forms what? Sorry, my computer's acting up. Come on, work with me, work with me. Yes, this always leads to the formation of a carbon cation. Good. And you guys do know that I need to beware of what when I form carbon cations?
Rearrangements.
That's right. Beware of, let's type that in. Beware of carbon cation rearrangements. You guys remember the 4 ways that carbon cation rearrange?
Methyl shift.
Yeah, methyl shift. Let's do hydride first since it's smaller. Sorry. Hydride shift. Methyl shift. What else? You guys remember ring expansion? And what's the 4th way? Yep, that's right. Resonance delocalization. All right. So mentally, in your mind, you want to keep these things present when you form carbon cations. Can that carbon cation rearrange? All right. What's the second step in a E1 mechanism?
Remove a proton.
Yeah, you're gonna extract the. I'll give you that. It's a combination of things, but you're going to. My cap is on. You're going to extract in a proton while forming pi bond, or you can say your double bond. All right, let's do an example of this. Can everybody see this okay in Teams? Is that yes or no?
Yes.
Okay. So reaction class 1, again, of alcohols is a dehydration reaction. And what's unique about dehydrations is that it's an E1 class mechanism that we know a lot about at this point in our careers. All right, I'm going to make this a little bit bigger because I want to put emphasis there. All right, let's do an example. Sorry, I don't know why I just keep asking for this mirror. I'm not mirroring anything. Okay. We used to have a lab where you guys dehydrate. I'm trying to figure out which compound it was. Oh, it's actually cyclohexanol. Let's do that. Actually, if you in my lab, I'm planning to do this, a variant of this reaction in labs. All right. This is typically one of our first labs for second semester organic. Things has changed a lot, but we'll talk about it here in class. All right, give me one sec. I'm just trying to change my settings here a little bit to how I like them. Oh, thank you. Sorry about that. Okay. Good. All right, good. If I take cyclohexanol, and I hope everybody's comfortable with the name there, right? It's a 6-member ring. So cyclohex, there's no double bond. So I say and I'll say all for the fact that it's an alcohol, right? And if I introduce to this acid, I'm going to use here H3PO4. Let's use that. That's phosphoric acid. And if I have heat, all right, give me one sec. I'm trying to pull over one of mine. All right, typically, you guys are going to see me use this for heat, this delta symbol, all right? So I'm going to put here parentheses heat. All right, so when you see that delta symbol, signal, symbol, can't get my words out. Thank you. Wow. All right, that's indicating heat. So a lot of times we don't write heat, we just write that delta symbol, all right? So when I heat this up, I'm going to form this as my product. All right, can anybody give me the name of that compound? All right, so we said that this is cyclohexanol, right? What's the name of the product that we just formed from the dehydration? Cyclohexene. Yep, double bond there. All right. So this is the classic way of doing a dehydration. All right, so this is classic. So typically, all you need to do a dehydration is have an acid with alcohol, all right? So we put here, we'll put here for note. Any acid would work. Yep. I'm gonna do the mechanism here shortly. Good question. All right, let's do the mechanism. It might be hard to see this if I don't know the chemistry yet, right? So let's do the mech. And this mechanism is a good one that we used to like to ask on tests, right? So you guys want to be prepared to draw this mechanism. Okay. So guess I'll be doing this all day. Those letters are a little too big for this. All right, so the first step of our mechanism involves a protonation step, all right? So I'll write that out here. That step one is our hydroxyl protonation. What does that mean? Anybody help me out? What does that mean that I'm doing a hydroxyl protonation? What does that mean? All right. Definitely something with the number of hydrogens. Anybody else?
Are you moving them?
Yeah, does it mean you're gonna be transferring the proton?
Okay, there's going to be a transfer. That's right. From where to where? Can you guys help me out? Say that one more time. All right. I'm just going to call this an acid. You guys know that's phosphoric acid. All right, help me here. What do acids like to do?
Donate protons.
Donate a proton, right? So if we're saying that the hydroxyl group is becoming protonated, all I'm really trying to say is that the OH group is adding a what to it now? Yeah, a hydrogen, right? Or a proton in a sense, right? And how do I get that? From something that loves to give away protons. And you guys tell me who loves to donate protons? An acid. So phosphoric acid is going to donate a proton. All right. This is where students, you want to remember how this mechanism works. Even though phosphoric acid is giving away an H, the mechanism has to start with electrons. All right. So what happens here is that the lone pair on the hydroxyl group is going to pick up that H. All right. Let's call that red. And I have to show the bond breaking between the H and the O here, right? All right, I'm going to try to make my own arrows here. See if this works today. All right. This is the complete steps for showing this hydroxyl group getting protonated. All right. And I see students sometimes get this tricked up. All right. So you want to convince yourself that you can make sense of these two things. All right. The lone pairs on the hydroxyl group here, we talked about that earlier, being nucleophilic, right? They don't mind using those electrons to do some work. All right. In this sense here, they're not attacking an electrophile. Instead, they're just gaining a proton. Right? So these lone pairs are going to grab this H, and I have to show the bond breaking between H and O, right? So how do I show that? I said that the two electrons that were shared between O and H now reside solely on oxygen, right? That's indicating that complete breaking of that bond. So now I'm going to get this molecule that used to have two lone pairs, now it has only one lone pair. I'm going to put two H's here. Actually, you know what? Those lines are not long enough for me. And this oxygen now has a formal charge that is plus. Right? Is everybody comfortable with that? How is that a positive charge in oxygen? Lost a lone pair, or you do your formal charge, right? Which is valence electrons minus lines minus dots. So oxygen has how many valence electrons?
8.
Not 8, but only not 6. That's the total electrons, but valence electrons are 4, right? Good. It's in group 4. All right. So I have 4 valence electrons. Oh, I'm so sorry. This is not, I did carbon. This is oxygen. All right. I'm so sorry. Oxygen is in group 16. I'm so sorry. I was thinking of carbon. All right. So I do have 6 valence electrons. How many lines do you see to oxygen? All right. 6 minus 3 is 3. And how many dots you see on the oxygen? 2. So 3 minus 2 gives me a positive what? 1. So this is why this oxygen has a plus charge. All right. Very good. What else?
But Dr. Cooper,
Go ahead. Go ahead.
can you explain where the H's came from like doing the first step?
Okay. Yeah, sure. Maybe I should color code. I'll give that a red color. All right. So are you okay with the fact that cyclohexanol already had an OH? So that OH here was already present. And the H that got added came from phosphoric acid.
Okay.
Yes. And the bond between the H and the O broke. Put this back here. The phosphoric acid has 3 hydrogens, 4 oxygens, and 1 phosphorus. Good, good. So my other product is what? What's the other product I could draw from this? I could draw this compound out, right? All right, I'm going to draw it in 2 ways here. And then we're going to talk about some terms that we saw in first semester, right? So typically, for things that are non-carbon based, and you guys know that I'm not too interested in inorganic materials, so I like to somehow not to draw them, or I would abbreviate those, all right? But that's the same compound as this. We'll talk about this here shortly. All right. So I'm not redrawing it when I already drew it out. I keep hitting that. All right, and hopefully you guys can recognize that those 2 compounds are exactly the same, right? So I just write this O out here, and I write PO3 with 2 H's, right? All right, there's some terms that I want to make sure you guys remember. Let's go backwards really quickly. All right, the product, and this first step is this acid-base chemistry. You guys remember acid-base chemistry? We covered that in the first semester, right? So I can have an acid and a base, and my products are going to be called what? What are the 2 potential products for every acid-base chemistry?
Conjugate base and conjugate acid.
That's right. Bingo. Very, very good. Very, very good. Which compound is the conjugate acid? Which compound is the conjugate base? This one right here? Yeah, that's right. This is the conjugate base. Very good. Which compound is the conjugate acid? Well, I think that's easy. It's the only other compound, right? This has to be the conjugate acid, right? So if we looked at the whole reaction, cyclohexanol is operating as a way. the base, right? So you guys do know the relationship. If I start in my reactant as a base, usually in the product side, I'm going to be now the conjugate acid, right? And if I start off as an acid in the product side, I'm going to be the conjugate base. Not too bad. Yes, no? No, yeah? All right, can you guys tell me while we're doing this, we can review some old things. Is this reaction favorable or not? How do you know if this acid-base equilibrium is favorable? What direction does equilibrium lie? You guys remember doing that?
Doesn't it have to do with the pK?
Yep, we need to know the pK values. Very, very good. So I'll give you guys the pK values. Oh man, phosphoric acid, I don't know its pK. For sure, it's like -2, all right? So phosphoric acid, I'll just give you the values. These are not normal values, and I'm estimating as well. This is gonna be a -2. This is a strong acid, I know it's a negative value, all right? And this is just a protonated oxygen species, all right? This is gonna have a pKa of around 3. So based off of these pK values, is this a favorable reaction? Or is the equilibrium favorable? Yep, based off of those two values for the acids. You guys remember?
Dr. Cooper, those values are given.
Yeah, these will be a chart given. Yes, right.
Okay.
To be honest, I don't know phosphoric acid's pK value off the top of my head. I'm guessing, but it should be in the negative range. A protonated oxygen is around that range as well. I think it's around 3. I don't have my notes with me. All right, so equilibrium always lies towards the larger value, right? So we'll say this. That's a base. Equilibrium lies towards the larger pK value, right? If that value is on the product side, we call the reaction what? Favored, right? If the large value is on the reactant side, we call that reaction unfavored. All right. And you don't have to memorize it. I try not to memorize it, but you have to. We'll give you pK values. You don't have to memorize the pK values. I used to have all my pK values down. All right. But this logic, I don't want you guys to memorize that. All right. This is kind of like hopefully common sense a little bit. Let's talk about it to make sure you guys are comfortable with that. Why is this the case? Why, if the large value is on the product side, we call it a favored reaction, right? Anyone has a good explanation?
Because that means that the reaction will occur naturally, like you won't need nothing to like make it go. Like it favors that direction.
That's right. Bingo. That's correct. So good. You guys got the logic that I wanted to make sure you had, right? I mixed these two things in the hopes of generating these products, right? So whenever the product becomes favorable, whenever I know that the products I'm seeing or the products that I want, I actually see in the flask, we always call that favorable, right? But when I mix two chemicals and I observe the reaction and I only see the starting reactants, then I know that the reaction hasn't occurred. So we usually call that unfavored. Now, you guys know something about kinetics. Sure, there's equilibrium, then there's kinetics, right? Kinetics tell you something about how fast the reaction works, right? So a lot of times there are reactions that happen really fast. And that didn't mean that when you mix the acid and base together, they didn't react. It just means that they react so quickly or they react in an unfavorable way to where you only see reactants back, right? So I want to make sure that students don't think that because I added these two things together, they didn't react if I just see reactants. They did react, but as soon as you form the conjugate acid, it's so strong that it donated its proton back to generate the reactants, okay? So good. This is just a review, and I'm hoping this just kind of makes things make a little bit more sense. All right, this is relying on skills that you already know. All right. So this reaction that we just did is favored, right? And this is why I typically give this arrow here, right? This is not right. I should put an equilibrium arrow here, but I know that this reaction is so favored that I'm going to generate this in my mechanism. So I just give it a full arrow. All right. Are we cool with that so far? All right. So I'm going to recopy this. Well, I don't have to recopy this. I'll take this part. All right. Part 2. Loss of water. Okay. Did I form water anywhere? Do I have water anywhere in my compound? I do. I do. Where's the water at? Right here. This looks like water, doesn't it? All right. I'm going to say it looks like water because I'll give you the official name here. Looks. All right. Whenever I have this positive oxygen species, these things are known as Alcorn ions. Right. And this Alcorn ion can lose water. So how do you think that happens? Yep, how do I lose water? Could be. Another way to think about this is that water is a great leaving group. Right? And what do we know about leaving groups? Leaving groups like to leave, right? So no different if this is the regular halide that you guys had last semester. If I had bromine here and I actually do a E1 mechanism, what's the first thing you would do? Knock off the leaving group. You will make the leaving group leave, right? So the only difference with a dehydration reaction is what? First, I need to form what? First, I protonate to form water, and then water becomes my what? My leaving group. Bingo. All right, so let's knock off our leaving group. How do I do that? Okay, heat is going to do it definitely in the flash, but I want to show the curved arrows. You all right? You all right? I'm going to start my arrow. What in the world? At the bond between carbon and OH, right? I start here. And I have my arrow in on the oxygen. Let's zoom in here a little bit. Yep, I'm showing the leaving group leaving. That's right. Right. I'm going to zoom in. Can you guys see that? All right. So I start my arrow at the bonds, and this is something I wanted to talk about last semester. I just kind of ran out of time. So I'm hoping this semester I'll be able to do a little bit more detailed work on mechanisms. All right. This is saying that there's 2 electrons shared between carbon and oxygen, right? These electrons are not going to be shared anymore. My leaving group is going to leave, and when it does, it takes the 2 electrons with it. So all I'm saying is that this bond breaks with the 2 electrons now going exclusively to oxygen, right? So I'm going to draw that product out to confirm to the person that's reading my mechanism that water has left, right? So I'm going to draw my carbon species without the oxygen stuff now. Right, that bond is no longer present.
Quasi red heart. FaceTime video.
Oh, somebody has their mic on and I got a call came up. I can mute you, JC. Did you fall asleep on me? Miss Curry. All right, I can mute you, Miss Curry. All right, so I lost water. Let's back out a little bit. Let's take a look at this full thing. All right, water just left. I formed a what species here?
Carbon cation.
Carbon cation. And I have a byproduct. What's my byproduct? H2O, which is, you guys know for sure as, right? Okay, good. What do you think my last step is then? All right, step 3 is a proton attraction with pi bond generation. Okay. I'm going to take my carbon cation, and maybe I should put that up top here. I don't know why this board is doing that. What type of carbon cation is this, by the way? How would I classify that? It's benzylic, right? It's allylic. This carbon cation, how would I classify it? There's no classification for it. Okay, I'm just asking, I'm going back here for the carbon cation. I'm sorry. Can you guys classify that for me? So if I look at the carbon that had the plus, right? I'm going to point to with this thing here. How many carbons are attached to it?
2.
2 carbons, right? Carbon here, carbon there, right? Is there a double bond near it? Is there a pi a benzene ring near it. No pi bond, so it's not allylic, right? And there's no phenyl ring, so it's not benzylic. So this is just kind of your regular type. And because there's two carbons, we call this what type of carbon cation?
Secondary.
This is a secondary carbon cation. Right, very good, very good. All right, I just wanted you guys to lose that. All right, this, I'm gonna use my conjugate base here. Is everybody comfortable with this? This is still a base.
Before you keep going, what is a proton abstraction?
Yep, I'm removing an H plus.
Okay, so is it supposed to be extraction or?
Oh yes, I'm sorry. I'm using one word too. That's abstract, not abstract. I'm sorry.
Okay.
Boy, just saying everything that comes to mind. Yes, let me get this spelling right. Step 3, I need to form a double bond now. Give me. Okay, good question. Let's back up. All right, someone's trying to keep track of everything. And the way it could be going could be a bit confusing. So let's go back and look at everything at once if we can. Can you guys see things if I do it like this? All right, so overall, let's go back and think about what a dehydration is doing. I'm sorry. Okay. Sorry. I was trying to make sure that I was thinking about something correctly and I had the spelling right. All right, abstract is right there. All right, in my dehydration, I have an alcohol that's going to form a double bond to make an alkene, right? So I need to think about those steps. Step 1 is just forming water, right? So I'm going to protonate the hydroxyl group to form this osconium ion, or in other ways, it has water, right? Step 2 is that I have to knock off water now, right? If I look at the product here, did I have water present on the ring? I did not. So I needed to do that step. I need to protonate that, and then they can leave as water. And you brought up a very good point. All right, Ms. Hollenberg. These reactions work when you heat them because water can move into the gas phase, right? So all you do when you heat these things up is produce steam. And this keeps the reaction moving forward. Right, now that we have the water off, I do need my step 3. What is missing? My double bond, right? So how did this form the double bond? This is how we're going to show it in step 3, right? So I'm not using water anymore because water is leaving out of the flask, right? It's not really present. But my conjugate base is always here, right? And what does the bases like to do? You guys tell me, or you guys can tell me. What does a base prefer to do? If an acid donates, that's right. Bases like to accept the proton. Okay. All right, so I'm going to remove, or I should say proton removal. Let's just do that to make, so I don't confuse anyone and myself. All right, so how does that work? I'm going to use the pre-stock arrows for this. All right, my conjugate base is going to grab a proton. And again, a proton is just a hydrogen atom with no electrons. So what happens to the electrons that were shared? They're going to collapse to form a what? A pi bond. Yep, the H is always there, right? Line structures, each carbon has two hydrogens. I've just drawn one hydrogen. Yep. Give me one sec. Let me draw the full product out, and then I'll try to back up. Good questions. Got some questions coming. Good. Mm-hmm. Actually, it doesn't matter. All H's are equivalent here. That's a good question too. Does it matter which H? It doesn't. All the H's on this molecule are exactly the same. In other examples, I guess you guys know it's coming. There is a choice. You want to choose the H, the better H, or the more acidic H. We'll talk about those a little bit later. Man, I was hoping to do a little bit more than this today, but it's all right. It's all right. So I'm going to form cyclohexene plus my product, which is phosphoric acid is going to be back. All right. So phosphoric acid here is catalytic. That means I can regenerate it in the reaction. So I don't have to use a full stoichiometric amount. I can use like half, and I will always generate enough phosphoric acid to keep the process going. All right. Any questions there? So the question that came up, can I try to talk more about this? And we can do that. Phosphoric acid needs a proton. All right. So again, you have to know what a proton is. A proton is just the H atom with no electrons. So phosphoric acid is going to grab it. It's saying, I'm going to take that H, right? However, this H was bonded to carbon, right? That means that it was sharing electrons with something, right? So the mechanism has to reflect what happens to the sharing, right? You had a dollar bill at one point, right? But you had a deposit in the bank. But there's a process that happened between the money getting into the bank and you having the money, right? It's kind of had to be some exchange, right? So we have to show that exchange process. So I'm saying that phosphoric acid just grabs the H. That's all I can show it is doing. But I have to show the bond breaking between carbon and hydrogen. Okay? Now, uniquely, because there's a carbon cation next door, I can form a what there? A pi bond, right? If there was no carbon cation, typically you would just put a lone pair there, right? You say, oh, these two electrons just reside on carbon. But because it's a carbon cation next door, I can make another bond, right? So this is how I get that pi bond here. All right, does that help?
Where you get the H4?
Oh, there should be 3 H's on here. I'm sorry. That's my fault. Let me go back, phosphoric acid. No, I had it right. It's not 4 H's here. I got these numbers transposed. All right, thank you for correcting me there. All right, I had drawn phosphoric acid wrong, I'm sorry. Okay, so I wanted to show here that you get that double bond back. Because there's a carbon cation next door, this allows me to make an additional bond to that carbon, and I get the alkene. Okay. Does that help answer your question?
I'm looking and I'm trying to make sure I understand. So when the hydrogen bond broke, the proton went to the acid, and that's how it formed the double bond.
That's a base, but yeah, it went to the base. Yep. And these electrons here are now shared right here. Good. All right, next class, we need to talk about the other reactions. All right, and we can do each examples of those, and then I need to give you some real life examples. All right, we're gonna start. I'm gonna give you some random alcohols, and we're gonna have different conditions, and you're gonna predict the products. All right, we need to start getting into that next class. All right, this is good. This is all right. We just class is like the third class. All right, I will send these to you guys for dehydrations.